To truly understand the nature of reality, we must first investigate what the world around us is fundamentally composed of. Initially, we believed the universe's building blocks were atoms, tiny, indivisible units of matter. Yet, as we probed deeper, smashing atoms together using increasingly powerful particle accelerators, we discovered that atoms could be broken down into smaller constituents: protons, neutrons, and electrons. Delving even further, we found that protons and neutrons themselves were made of quarks, and that electrons belonged to a family of particles called leptons. Our picture of matter evolved from solid, featureless spheres to complex, layered structures brimming with intricate subatomic entities. At present, quarks and leptons appear to be the smallest known building blocks of reality, fundamental particles that cannot be broken down further using our current experimental methods. But there's a catch. These particles are inconceivably small, so much so that no light-based instrument can ever see them directly. Electromagnetic waves, the carriers of information that let us perceive objects, are simply too large compared to these minuscule particles. The waves cannot bounce back with meaningful detail when interacting with something so tiny. Consequently, while we know elementary particles exist, we've never truly observed them in the conventional sense. We rely on indirect evidence, detecting signals from their collisions, analyzing their footprints in particle detectors, and interpreting subtle hints they leave behind. To tackle this quandary, physicists developed a theoretical framework that treats elementary particles as point-like objects. No size, no shape, just locations in space. This elegant simplification allowed them to define these particles mathematically, predict their behaviors, and calculate their properties with astonishing precision. For instance, researchers have measured certain quantum attributes of the electron with mind-boggling accuracy, on the order of 1 part in 10 trillion. This approach revolutionized science and technology, underpinning much of our modern world, from computers and lasers to medical imaging and GPS systems. Yet, for all its success, the point-particle model remains incomplete. Our understanding of the cosmos, while immensely useful, still contains glaring gaps. Enter the great puzzle of modern physics: general relativity and quantum mechanics, the two pillars of our understanding, do not fit together seamlessly. General relativity, championed by Albert Einstein, beautifully describes the cosmos at large scales. It weaves space and time into a four-dimensional fabric whose curvature explains gravity. Quantum mechanics, on the other hand, shines at microscopic scales, revealing how particles behave in weird and wonderful ways, governed by probabilities and uncertainties rather than classical certainties. These two frameworks function splendidly within their respective realms, but clash when combined. Attempts to apply both at once, say, at the center of a black hole or at the very beginning of the universe, lead to nonsensical infinities and mathematical breakdowns. The crux of the problem lies with gravity. Of all the fundamental forces, electromagnetism, the strong and weak nuclear forces, and gravity is the odd one out. It is by far the weakest, yet it dominates at large scales, holding planets, stars, and galaxies together. On the quantum scale, however, gravity's feebleness makes it virtually irrelevant, and attempts to describe it with the same quantum tools that successfully handle other forces run into trouble. We predict a hypothetical particle called the graviton to mediate gravity, but when we try to calculate what happens when two gravitons collide, we end up with infinite energy concentrated into an impossibly small space. In other words, something about our current picture is woefully incomplete. We know gravity exists because we observe its effects on enormous structures, celestial bodies moving in orbits, light bending around stars and galaxies, and universes evolving over billions of years. But at the tiny scales of quarks and leptons, gravity's whisper is lost in the roar of other forces. This is where string theory enters the scene. Conceived as a bold attempt to unify quantum mechanics and gravity, string theory suggests a radical shift in perspective. Rather than treating particles as zero-dimensional points, consider them as one-dimensional strings of energy, thinner than anything we can conceive. These strings would be incredibly small, around 10 to the 33 centimeters. To provide context, this is a millionth of a billionth of a billionth of a billionth of a centimeter, an incomprehensible scale where normal intuition fails. Unlike a ball that can only move forward and backward, left and right, up and down, these strings can vibrate in multiple dimensions. String theory initially required 26 dimensions, though more advanced superstring theories have cut that number down to 10. Even then, that's 6 dimensions beyond the 3 spatial ones and 1 temporal dimension we experience. Where could these hidden dimensions be? According to the theory, they might be curled up, compactified so tightly that they remain invisible to us. Think of a power line seen from far away. It looks like a simple line, effectively one-dimensional, but to an ant crawling on its surface, the power line is a 2-dimensional cylindrical surface. Similarly, what we perceive as 3-dimensional space might hide additional dimensions twisted up at scales too small for our eyes or instruments. The vibrations of these strings through these hidden dimensions would determine the fundamental properties of particles, akin to how different vibrational modes of a guitar string produce different musical notes. Instead of notes, these quantum strings produce the characteristics, mass, charge, spin, of particles like photons, quarks, or even the elusive graviton. By replacing point particles with strings, many of the infinite energy problems vanish. Collisions between these tiny strands of energy don't lead to nonsensical infinities. String theory thus offers a mathematical framework that might allow quantum gravity to be described consistently. Moreover, it predicts a wealth of new possibilities, hypothetical particles like axions to explain dark matter, scenarios for dark energy, new insights into the Big Bang, and potentially even new universes. Indeed, one of the striking implications of string theory is the idea of a vast multiverse, with countless pocket universes shaped by different ways of compactifying dimensions. Each might have its own version of physics, its own array of particles, and its own laws of nature. Still, major challenges remain. We currently lack the experimental capability to test string theory's predictions directly. Some skeptics argue that without the possibility of falsification, an essential criterion in science, string theory treads close to pseudoscience. Others counter that just because we can't test it now doesn't mean we never will, citing historical parallels. Einstein himself doubted that splitting the atom to harness nuclear energy was feasible, and yet today, nuclear power plants light up entire cities. Another issue is complexity. Even if we assume string theory, or its later refinement, M-theory, is correct, understanding it fully requires mathematical tools beyond what we have developed. M-theory unites the different versions of string theory into a single, cohesive vision, suggesting they were all facets of the same underlying structure. However, M-theory is still being explored. We've only scratched the surface of its immense mathematical landscape. Advances in pure mathematics computational power, and perhaps even new theoretical breakthroughs will be needed before we can confidently say we have a theory of everything. In the meantime, physicists continue to refine string theory, study its predictions, and search for indirect hints that could point toward its validity. For example, if one day we detect superpartner particles predicted by supersymmetric versions of string theory, or if we find subtle anomalies in the cosmic microwave background radiation that match string theoretic models, we might gain confidence in the theory. Likewise, improvements in particle accelerators, neutrino detectors, gravitational wave observatories, or even dark matter searches might yield data supporting string theory's grand claims. As it stands, string theory is a daring attempt to peer behind the curtain of reality, to unify the infinitely large and the infinitesimally small, and to reveal the deep architecture of the cosmos. Whether it will ultimately guide us to a complete understanding or be replaced by an even more compelling framework remains unknown. Nonetheless, the mere pursuit stretches our imagination, challenges our intellect, and may one day revolutionize our understanding of existence. What do you think? Is string theory our best shot at a final theory of everything? Will we ever build the tools or discover the phenomena needed to prove it right or wrong? Share your thoughts in the comments, and don't forget to subscribe and turn on notifications. We'll continue exploring the mysteries of the universe, pushing the boundaries of knowledge, and seeking answers to the profound questions of who we are and what the cosmos is made of. Thanks for watching.